In this video, we will continue studying nodal analysis. Today, we will consider a case in which we have a voltage power supply between two nodes. This power supply is not between a reference node and the other nodes in the circuit, but it's between two nodes where we do not know the voltage. For the reference node, we already know the voltage, so therefore, this is not the case. That case was discussed in the previous video. To explain nodal analysis with a voltage source between two nodes, we will consider this circuit. Here I have a reference node, which we have chosen to be the node in the bottom, and the voltage at this point is 0 volts. And we have two other nodes, as you can see in the circuit, V1 and V2. The voltage at node 1 is V1 and the voltage at node 2 is V2, and these are the two quantities that we want to find using nodal analysis. The first step is to choose the currents that are flowing into each node. So let's say I'm going to assume the following directions. So this is current I1 flowing into node V1, current I2, I3, and I4. So there are four different paths through which the current can either flow into or out of node 1, and I have just given them some names, and I have chosen some directions for the currents. At node 2, I will assume that I4 is still flowing in the same direction as we chose previously. I3 is also based on our previous choice. Here I will have I5, and the current in this branch is, let's say, I6. So these are our different currents that are either flowing into or out of our nodes. The next step is to apply KCL at each node. So KCL at node 1, so I'm just going to write 1. It says that the current in must be equal to the current out. So the current flowing into the node must be equal to the current flowing out of the node. As such, I can write now the equation that I1, which is current entering node 1, so I1 plus I4 must be equal to I2 plus I3. So I1 and I4 are entering the node, so that's why I put them on the left-hand side of the equation, and I2 and I3 are leaving the node. Now we want to write these currents in terms of node voltages. So if we look at the circuit, we can see that I1 is 5 ampere. So maybe I can say here that I1 is equal to 5 ampere. So that is fixed by the constant current source. I2, on the other hand, I2 is equal to the high voltage minus low voltage divided by the resistance, right? So the high voltage is V1, the low voltage is 0. So therefore, I2 is V1 minus 0 divided by the 1 ohm resistor. So it will be V1 divided by 1, so which is equal to V1. So this is the current I2. I3 similarly can be written as it's V1 minus V2 whole divided by the 2 ohm resistor. Now the problem is with I4. We cannot write an equation in terms of node voltages for I4. Like for example, if I try and say that I4 must be equal to, because it's flowing from node 2 to node 1, so it should be V2 minus V1 divided by what? We cannot tell. So we cannot calculate I4, or we cannot represent I4 in terms of the node voltages. Also, the current I4 is produced by the constant voltage supply. That voltage supply can either produce a small current or it can produce a large current. It depends on the rest of the circuit. So this voltage supply will produce the amount of current necessary to keep the voltage difference between V1 and V2 equal to 10 volt. So the purpose of this voltage supply is to keep the voltage fixed between the two nodes, and whatever current is needed to ensure that this voltage supply will produce that much amount of current. So therefore we cannot actually calculate I4. So to resolve this situation, we will consider something called a supernode. So I have redrawn the circuit over here, and now we will define something called a supernode, in which we will treat both of the nodes together as a single node. So let me draw this outline. So this outline, which encloses node 1 and node 2, this will be our supernode, and we will treat it as a single node. Now let's apply KCL to this supernode. Again, KCL says that the current entering the node must be equal to the amount of current that is leaving that node. Now I see that I4 is leaving the supernode at V2 and I4 is entering the supernode at V1. So we do not need to include this because it will just cancel out, because what it says is that the amount of current I4 leaves the supernode and the amount of current I4 enters the supernode. So therefore I4 will have no effect on the rest of the calculation. Similarly, I3 leaves our supernode at this point, and I3 enters the supernode at this point. So therefore, again, I3 will be coming into the node and leaving the node. Therefore, it will be present on both sides of our equation, and therefore it will just cancel out. So we do not need to consider I3 and I4 because these terms will be present on both sides of the equation and they will cancel out. The rest of the currents we will consider. So therefore, the current entering the node is I1. So the current entering the node is I1, and the current leaving our supernode, those are I2 plus I5 plus I6. So these are the three currents that are leaving our supernode. So now we need to write these currents in the form of voltages. First of all, I1 is 5 ampere. So I1 is 5 ampere. I2 is V1 divided by 1 ohm, so which is just V1. I3 we do not need to consider. I4 we will not consider. I5 is V2 minus 0 divided by 3. And finally, I6 is V2 minus 0 divided by 4. So these are our different currents. Now let's put these values in our KCL equation. Therefore, we have 5 ampere is entering. It is equal to I2, which is equal to V1 divided by 1 plus V2 divided by 3. That's I5 plus V2 divided by 4. To simplify, I will multiply by 12 on both sides. 12 times 5 is 60. 12 V1 plus 4 V2 plus 3 V2. Now combining the same terms, I will have 12 V1 plus 7 V2 equals to 60. Now this is my first equation that I got from the supernode. And V1 and V2 are the two unknowns that are involved. To solve this circuit, because we have two unknown voltages, V1 and V2, we will need two equations. But we have already used both of the nodes and got one equation. The second equation is very easy to see, is already given to us by this voltage source, because this voltage source is actually telling us the relation between V1 and V2. If I say that according to this source, the voltage at V1 is 10 volts higher than the voltage at V2, and you should be okay with that, because the voltage source, the job of this voltage source is to ensure that the voltage on the left is 10 volts higher than the voltage on the right. So therefore I can say that V1 is 10 volts higher than V2. So it's V2 plus 10, correct? So V1 is 10 plus V2. Now this is our second equation, okay? So we will say that this is our second equation, and now we have two equations and two unknowns. From this equation, I already have the value of V1, which is 10 plus V2. I will put this value in the second equation. So V1 is 10 plus V2. So I will have 12 times 10 plus V2 plus 7 V2 equals to 60. This is 120 plus 12 V2 plus 7 V2 equals 60. 12 and 7 is 19. 19 V2 is 60 minus 120 is negative 60. Therefore, V2 is negative 60 divided by 19, and V2 is equal to minus 3.158. Minus 3.158 volts. So this is the voltage at node V2, or node 2, sorry. So we found this voltage V2, and it turned out to be negative. Okay, so negative means that it is the voltage at this point is less than the voltage at the ground. So the ground is actually at a higher voltage than the point V2, which means, as we remember, that the current always flows from higher potential to lower potential. So this means the current will be flowing from the ground to V2. So I5, we should expect that it should be flowing in the opposite direction, as well as I6. These two should be flowing in the opposite direction. All right, so we already found V2. Now the next step is to find V1, and we know that V1 is 10 plus V2. Therefore, V1 is 6.842. 6.842 volts. This is the voltage at node 1. Now we got the two voltages, and now we can check if these voltages are correct. All right, so here I have redrawn the circuit with the two node voltages written as indicated by the arrows. So we have 6.842 volts at point 1 and negative 3.158 on node 2. Now I want to see if these values are correct, and we can check that by calculating the different currents and see if the current entering a node equals the current that is leaving that node. So in this circuit, I know that I1 is 5 ampere. So 5 ampere is entering node 1. Looking at the circuit, I have 10 volts from point 1 to point 2, or node 1 to node 2. I have 10 volts over here. And you can see that the 2 ohm resistor is connected in parallel to this 10 volt supply, which means the voltage across this 2 ohm resistor will also be 10 volts. Correct? This will be 10 volts, which means the current I3 must be equal to 10 volts divided by 2 ohm resistor. So I3 is 10 divided by 2, which is 5 ampere. And 5 ampere is leaving node 1. Now you can see that 5 ampere is entering node 1 and 5 ampere is leaving node 1. Now let's look at I2. I2 is the voltage at node 1 divided by the 1 ohm resistor. So it is 6.842 divided by 1, which is 6.842 ampere. So this is the amount of current that is leaving node 1. So I can say that I2 is now 6.842. All right, so let's take a look at these three currents. I3 is 5, I1 is 5, and I2 is 6.842. Now I1 and I3, they completely cancel each other because 5 ampere coming in, 5 ampere going out. So net current going in or out is now 0. I2 is 6.842 going out. So this means 6.842 amperes are going out of node 1, which will enforce us to say that I4 must be equal to 6.842, so that the amount of current coming into the node is equal to the amount of current going out of the node. So because of this, the voltage source will produce 6.842 amperes, which will go into node 1. So now I can say that I4 is 6.842 ampere. Now this is something that we didn't know earlier. If 6.842 current is coming into node 2, we must also agree that the current that is flowing from node 2 into the negative of this supply, that current must also be equal to 6.842 amperes. So you see at node 2 now we have 6.842 amperes going out. And also because I3 is entering this node, so we know that this is 5 ampere. 5 ampere is coming into the node and 6.842 leaving the node. Let us calculate I5 now. I5 is V2 minus 0 divided by the resistance value, which is 3 ohms. We calculated V2 and found that it is negative. And V2 is negative 3.158. So we have negative 3.158 divided by 3 ohms, and which equals negative 1.0527. This is I5. Now you see I5 turned out to be negative, which means I5 is actually flowing in the opposite direction, not the one that we assumed. We assumed that I5 is flowing from node 2 to the ground, but in reality, the current in this 3 ohm resistor is flowing in the opposite direction. So the current in the 3 ohm resistor is actually going from the ground into node 2, and the magnitude of that current is 1.0527 amperes. Similarly, I6, we can now calculate I6, which would be equal to V2 minus 0 divided by the 4 ohm resistor, I believe. So it's 4, which is minus 3.158 divided by 4, and that is equal to negative 0.7895. This is I6. So now we got I5, I6, I4, I3. So now we can check if KCL is satisfied at node 2. So at node 2, 5 ampere is current coming in. So let me redraw it. So I have redrawn part of the circuit, which is just focusing on node 2. And you can see that the amount of current coming into this node is this 5 ampere. And this I5, which is 1.0527. And this current, which is 0.7895. Now, to confirm if KCL is satisfied, these three currents, when I add them together, they should be equal to the amount of current I4, which is leaving the node 2. And you can add these three values, and it is exactly equal to 6.842, which means KCL is satisfied at both nodes. So therefore, these voltages that we calculated using the super node, 6.842 at node 1 and negative 3.158 at node 2, these are correct node voltages, and they satisfy all the KCLs and all Ohm's laws everywhere in each resistor. This completes our node analysis method. I hope you enjoyed this video. If so, please consider subscribing to my channel. That's it for now. I will see you next time, and bye for now.